Hey, welcome to Design Day. We are Team 25505, sponsored by Paragon Space Development Corporation. We are working on the Paragon Lunar Unmanned Super Heavy. My name is Humberto Rojas. I'm the systems engineer and the team lead.
Hello, my name is Adrian Torres, and I am a mechanical engineer.
Hi, my name is Nicholas King, and I am an aerospace engineer.
Hi, my name is Rami Al-Khudaidi. I am an electrical and computer engineer.
Hi, my name is Justin Dewey, and I'm an electrical and computer engineer.
Hi, my name is Zach Leon Guerrero. I am a systems engineer and procurement lead.
Given the technological advancement in launch vehicle capabilities and the constant search for interstellar resources, companies have begun research for a lunar lander capable of setting up permanent infrastructure on the moon to achieve these goals. Plush is the perfect solution, providing unprecedented cargo delivery potential whilst capitalizing on current active technologies. As of early 2025, the largest payload ever delivered to the moon was 5,500 kilograms aboard Apollo 17. Plush is theoretically capable of delivering up to 40,000 kilograms, an increase of approximately 730%. Plush is intended to pioneer the settlement of permanent infrastructure on the moon. The objectives of the project are to create a comprehensive CAD model for the structure and frame of Plush, as well as prototyping a subsystem, which came to be our reaction control subsystem prototype demonstrator. Major requirements driving the conceptual system design are the following. The lunar lander shall withstand the SpaceX Starship Super Heavy launch profile. The lunar lander shall not exceed a total wet mass of 200,000 kilograms. The lunar lander shall fit within the launch vehicle. Now, major requirements driving the system design for the reaction control system prototype are as follows. The prototype shall return to its initial spot within 15 seconds. The prototype shall use high-pressure air to achieve 2D movement and rotation. The prototype shall be fully contained with its frame. All requirements listed in our requirements document deliverable have a method of verification as analysis given the conceptual nature of our project. Our deliverables are divided up into three parts. The first is a requirements document which clearly defines a set of requirements for the lander structure and frame, landing stability, and shock absorption. The second deliverable is a conceptual design report which summarizes the proposed high-level design, including landing gear, primary structure, launch vehicle interface, and cargo bay organization. And our third deliverable is a presentation of findings which concisely presents the project's results, challenges, and next steps.
To be able to design the lunar lander, we had to work backwards, starting from our launch vehicle, SpaceX Starship Super Heavy. After deciding on the launch vehicle, the immediate constraints placed on our lander were dimensional, as we must fit within the payload bay. This spearheaded the design along with the expected cargo capability. Very shortly after setting dimensions, we conducted trace studies on material and vertical versus horizontal landing orientation.
All requirements for the conceptual design of our lunar lander were verified, ranging from the constraints imposed by the launch vehicle to the payload capability, all the way up to the cargo bay division and organization.
The RCS, or Reaction Control System, is a key component of any spaceship. It is what allows a spaceship to remain oriented in the correct direction for such maneuvers as burns or landings. Without an RCS system, your rocket is unable to maneuver itself to avoid rocks in landing or to maneuver towards the proper burn location. In order to figure out what pressure we needed to push through our nozzles, there are a number of calculations to be done, including the cross-sectional area of the hose and what the friction of the surface is. In our first round of calculations, we failed to account for the fact that the size of the tubing was given for outer diameter instead of inner diameter, leading to no movement due to lack of force. One of the proposed solutions on how to make sure that our prototype could move was to switch from high-pressure air to electronic ducted fans, or EDFs. After a trade study found the EDFs to be unviable, we switched back to using high-pressure gas and used pressure washer nozzles to columnate the air, which did allow for movement of the prototype.
Here you are looking at our reactional control system prototype. Our RCS system is a small mobile prototype that's moved on a flat surface using a compressed air. We use 8 solenoid valves to push the box in different directions. The valves are driven by MOSFETs, powered by batteries and controlled by an Arduino. We also use a distance sensor and gyroscope to measure how far the box is from the center and how it's oriented. In the software, we used PID controller on the Arduino to process the sensor data and decided which valve to activate it for how long. This helped the system correct its position and its move smoothly.
So, my role in the development of this project was to create the PID control algorithm that will model the reaction control system in our spacecraft. This will be loaded into our prototype to demonstrate movement. We first started with a one-dimensional control algorithm and then moved to two-dimensional and rotational with corresponding testing at each phase. We used common Arduino libraries to help us interface with our external sensors, and we also generated 2 custom structures to help us track our positional state and the PID control calculations. The software consists of a main driver sketch along with the state structure and PID structure, sensor reading and processing algorithm, control processing algorithm, and thruster output control algorithm.
The general theme of our problems in this project were how do we optimize our system? Even if it worked, the RCS prototype was inefficient or, at its worst, immobile. We had to further modify our system to increase movements such as reducing the weight of the frame, adding a low friction material to the environment, utilizing the Venturi effect to exchange PSI for velocity, and upgrading our nozzles, gyroscope, and accelerometer. We came to understand that individual components have a compounding effect on the end results, and that the exclusion or shortcomings of one can be the difference between success and failure. Overall, we have established the foundations for a lunar lander designed to carry heavy cargo and calculated its theoretical capabilities. We have also designed the Plush's reaction control system algorithm and have established functionality within a 2-dimensional model. There is still much work to be done for our sponsors and any future engineering teams assigned to this project. We wish them good luck.
We would like to thank our sponsor, Paragon Space Development Corporation, and the representatives Thierry Carrier, Craig Wellington, and Kathleen Lattin for providing us with this opportunity, as well as their input and support on the project. We would also like to thank the University of Arizona for providing us with resources and knowledge, as well as our mentor, Bert Schneider, for his support and advice during our work.